red line gives you the Arctic temperature in the background, like reference scenario, so just with greenhouse gases. And then the blue lines give you the Arctic temperature in the Arctic MCB simulations. So, yeah. And then on the bottom is the map of the surface temperature change you get around the Arctic. And the dotted line is where we actually do the injection, but it's where it's in the area of the dotted line, so between 60 and 80, but where there's no land and no sea ice. So it's only over the open ocean that we're doing it. So the amount of sea salt aerosol that we inject naturally varies seasonally because the amount of sea ice varies seasonally. And so the amount is given on that top plot. So we do this, so I've done this with the UK SM1, and Humuki ran two other sets of simulation with CSM2 and E3SM. So what we find is that all models do successfully cool the Arctic. There's about a factor of 10 difference in the required mass of sea salt aerosol injection. But again, in these types of models, it's not really the microphysics. You're not going to go to these types of models to have a good idea of the microphysics. You go to it to understand both the local and remote impacts of such an intervention. But this, yeah, and this factor of 10 difference is consistent with previous work in doing tropical injections. It's worth noting that the size of the aerosol emitted in UK SM1 is less than 2 times larger than in CESM2 and E3SM because we optimized the size of the aerosol for each model. Anyway, so that explains a large part of the difference in the mass. You can also look at the, ignore basically the table, but you can look at the shortwave forcing that you get. So these are fixed sea surface temperature simulations. It just gives you an idea of like how much forcing these aerosols give you. And so yeah, different models give you different amounts of forcing, but they all kind of do give you a very negative forcing in the summer. Yeah. And so what we find in these simulations, so obviously because we targeted the Arctic temperature, and broadly speaking, the distribution of Arctic sea ice follows that from the temperature, and what we find is that Arctic sea ice is mostly restored in these models. So the Arctic sea ice edge in the Arctic, oh, that's not correct. Yeah, so the black gives you the Arctic sea ice edge in the Arctic MCB simulation, and then the red is the sort of target, so the reference level. And you can look at the Arctic sea ice in different ways. I guess the bottom plot is the most interesting. So that's a seasonal cycle of the Arctic sea ice extent. The red is so what happens with just greenhouse gases. So obviously it goes down a lot, and the winter sea ice disappears in SSP245. The black line is the sort of reference or the target level of Arctic sea ice. And then the blue line is the Arctic sea ice under Arctic MCB. So basically it kind of works for sea ice, if you like. And that is true across the 3 different models. So yeah, as I said, I think the 2 first order Arctic sea ice follows from temperature, so it's natural that if by design you're like trying to fix the Arctic temperature, then the Arctic sea ice will be restored. In terms of precipitation, we find a robust decrease in Arctic precipitation in the winter. So all the plots on the left are the northern hemisphere winter precipitation change between the Arctic MCB and the SSP245 at the end of the simulation. So you see, and where there are dots, the changes are not significant. So you want to look at the patches where there are no dots. And so yeah, you can see basically a small decrease in precip in the Arctic in the winter for all of these models. But there's no other, at least according to these maps, very significant other changes in precip. You can then compare the precipitation to the reference periods. So the red lines give you the SSP245, and the blue lines is the Arctic MCB. So you get very large changes in precipitation, but that's caused by the greenhouse gases. If anything, the Arctic MCB, which is the blue line, brings you back closer to the reference period precipitation. You also get, in some members, quite steep, a large decline in precipitation in the northern hemisphere subtropics, but because there's quite a large spread in SSP245, that doesn't really come out as a significant amount. We do know from stratospheric aerosol injection simulations that if you do SAI focused on the Arctic, that because you're only cooling one hemisphere, that shifts the tropical rain belts in at least one model that did that. So this is giving you the temperature change from Arctic SAI, so that's if you inject aerosols in the Arctic stratosphere. And you get quite a large decline in precipitation in this Central African region, and where a lot of people actually really depend on rain-fed agriculture. So it's quite an important impact. So you can ask, like, okay, does Arctic MCB also cause these impacts? So we looked at the precipitation change in that red box down here. And what we find is kind of varies across models. In the UKS, so the black line is a reference seasonality of precip. The red line is what happens at the end with just greenhouse gases. And then the blue line is with Arctic MCB. In the UKSM model, you don't really see much change. In CESM2, you get a slight decrease in the SSP245, but not much of a difference between the SSP245 and Arctic MCB at the end of the simulation. And then in E3SM, you get an increase under greenhouse gases, and Arctic MCB just brings that back to the reference period. So kind of not consistent results for Sahel precipitation. And finally, you can look at the AMOC as well. So this is looking at the stream function of the ocean in the Atlantic. So we find that in all models, in two of the models, the AMOC declines slightly under SSP245. And Arctic MCB seems quite successful in two of the models in stabilizing the AMOC. In the third model, you don't actually get a decline in the AMOC, so Arctic MCB doesn't really affect it. It's really worth noting that in these models, the melting from Greenland ice sheet is not coupled to the ocean circulation. So please do take these results around the AMOC with a large pinch of salt. Finally, the other thing is it doesn't have a huge impact on global temperature. It has a larger impact on the UKSM because UKSM has a very large amount of Arctic warming. But if you look at the two other models, it's not huge. So it's worth keeping that in mind when you're thinking about sort of Arctic interventions. We're doing it mostly for the Arctic, and it doesn't really have a huge impact on the rest of the world, at least in terms of temperature. And finally, and something that I still need to understand a bit better, is that the cooling mainly happens in the winter, as is the case for both Arctic SAI, and as is the case for the observed warming under greenhouse gases. So, to conclude, we have evidence from volcanoes and cloud resolving models that aerosol emissions at high latitudes would brighten clouds and induce a negative forcing. This study is like first Earth system model intercomparison of Arctic MCB. It shows that in all three models, it could cool the Arctic and restore Arctic sea ice. Ignore that second point. There is a potential impact on tropical precipitation in some ensemble members, but it does not seem robust. However, there's a robust decline in Arctic winter precipitation, and it could slow the AMOC decline, but again with the caveats I mentioned. So finally, I will emphasize that these are highly idealized Earth system model simulations where sea salt aerosol are injected in all open ocean Arctic grid cells. So all the technical and governance feasibility of, like, for example, spraying sea salt in very dry and cold conditions, they're not considered in this study, so just take it for what it is. And finally, the preprint came out a couple of days ago, so if you want to read it, please look it up. Thank you very much.
Great. So we're going to have Q&A afterwards. So, Matthew, lots of questions have come up in my mind. So as a minimum, if the audience is going to be drying up of questions, I will fire grenades at you. But hopefully we've stimulated interest in the audience for the materials as well. We're now going to follow that with a presentation by Xia Li from the University of California in the USA. And the title of the talk is A Third Cloud Geoengineering Strategy to Manage Earth's Radiation in Polar Regions. So over to you, Xia.
Yes, thanks everyone for your patience, and thanks for stay until the last section for the conference. So I guess my talk, the main purpose is to introduce you a relatively new cloud geoengineering strategy with a purpose to manage the polar region radiation. So this is a collaborated project with my advisor, Jasper, and people from the UCSD, Ian Amato, and Lauren Catherine from Maryland. Okay, so talking about the geoengineering clouds, and if we categorize the clouds based on the phase, typically you would get either warm or liquid clouds or cold or ice clouds. And in the field, and there are a lot of already some strategies targeting on those two different types of clouds. So people might have already heard of those marine cloud brightening and cirrus cloud thinning over the past few days talks, so I'm not going to repeat here. But there's another regime for the clouds, which is mixed phase clouds. And this is quite unique because you can have both liquid and ice in the clouds. And most time you can see this type of clouds in the polar regions, in the lower latitude. And targeting on this type of clouds, and people have come up with this specific regime termed, specific technique termed as mixed phase cloud thinning, MCT. So that's what I'm gonna share with you today. And the first study targeting on this is by Diego Villalubia, who is sitting over here. Also has a postdoc here if you get a chance to also talk to him. So if there are already some, existing techniques, why I'm still proposing or addressing these new ones? Well, I'm a polar person. I love, working on polar regions. So I would wonder what is the existing techniques work for the polar regions, right? To understand this, we need to understand what is unique about these polar regions. Well, most of you already know, is roughly speaking, it's either polar night or polar day. So that means any strategies relying on reflecting sunlight would not be efficient during the polar night, such as MCB and SAI as well. The polar region is also a very cloudy place, but most of the clouds are low-level clouds instead of cirrus clouds, even though CCT might work in the polar regions. So to give you a sense of what type of different clouds are covered over the Arctic region, you can tell from the satellite, most of the clouds are covered by low-level clouds, and the cloud fraction is more than doubled compared to the high-level clouds. And if you get a chance to do field campaign, you would see this extensive low-level clouds covering or sitting here right over the Arctic Ocean. So that means maybe the mixed phase clouds would or might work. So based on the satellite data set, again, if we check the cloud radial effect over the Arctic region, and we look at the top of the atmosphere and the surface, and we will see based on the total cloud radial forcing, and most of the year, the clouds are warming the surface except for a short period during the summertime, and at the top of the atmosphere, the clouds are cooling from an extended window. But what I really draw your attention is this polar night months. So you see the clouds are warming both the surface and at the top of the atmosphere, and mainly through the long wave warming. So does it work from the perspective, microphysical perspective? And here is a nice figure I borrowed from the paper. And imagine we are having those, mixed phase clouds sitting over here. And what we can do is similar to the mixed cirrus cloud thinning, but except we are dealing with those super cold liquid droplet in the clouds. So if we inject the aerosols such as mineral dust, and it can serve as quite efficient as nucleating particles, and potentially could glaciating those super cold liquid clouds and turn those liquid drops to the ice crystals. And that's going to stimulate the WBF process, right? The ice crystals is going to grow rapidly at the expenses of the liquid droplet. In the end, you will have modified clouds with reduced cloud optical depth and also hopefully reduce the cloud cover. And what does that mean is in the polar night, without the solar radiation, those ice-dominated clouds would be more transport for the surface long wave emission from the surface. So you would have allow more long wave to be emitted to the space and induce a cooling effect. All right, so potentially it might work. And besides that, I also want to draw your attention to some other potential benefits for this MCT technique. First of all, the clouds are quite low. It sits typically below 3 kilometers, so it's quite accessible. And the overseeding issue, like what would happen in the CCT, is likely smaller. And also, those might potentially address what people call the Arctic residual warming from other techniques. If we combine, for example, the SAI and this should be MCT. And another point is those aerosols, especially from the CCT technique, they eventually might fall and potentially reach the level of the mixed phase clouds and stimulate this mixed phase cloud thinning process anyways. And again, it's relatively speaking original cooling technique and potentially would have fewer side impacts. Okay, so based on this might be a very selfish proposal, but I would love to extend the SRM to a little bit broader name, such as ERM, to include the studies that address the long wave perspective. So, like the MCB or the SAI, people like to find an energy, right, in the real world. Do we have any energy in the real world for the mixed phase cloud thinning? The answer is they are. So this is, people are very smart to find this industrial aerosol hotspot, for example, right here. And you would see right downstream of this industrial aerosol hotspot, and you would see a reduction of those cloud cover for these massive low-level clouds. And this is during the nighttime, and you might be able to see it more clearly during the daytime. The clouds are dissipated and the cloud cover are reduced significantly because of the aerosol perturbation downstream of those industry plants. And this study very nicely, they identified almost all those industrial hotspots over the high latitude land area. And to give you a statistic sense, and what they concluded is downstream, compared to downstream of this industrial hotspot, you would get reduce the cloud cover and reduce the cloud optical depth, and reduce short wave reflectance, and also increase the long wave radiance. So that's what we hoped to happen for the Arctic region for mixed phase clouds as well. So this is very nice evidence. So put back to all these strategies together in the context of polar geoengineering, and the way I organize them is to put them into two groups. One is the summer focused or shorter wave focused, or other one is the winter focused or the infrared focused strategies, including MCB. And one of the interesting aspects of this work, or what I'm interested in, is how this cloud geoengineering could help to restore the sea ice loss, like Matt has mentioned in his talk for the MCB, for example. But those two types of techniques, they are really handling the story from different angles. What I call is the sink-based, where you restore the CS loss by refreezing the open water. For these summer-focused strategies, well, for winter-focused strategies, it's different because we're restoring the CS by making them thicker so they can survive through the melting season. So it's source-based. So for this talk, I'm going to take a little story. Is by asking this question, is if we give the same forcing for each this strategies, summer focus versus winter focus. So what was the response for the global mean surface temperature and CS coverage? And the idea is to use a hierarchy of modeling to do this work, but to start with, we can do something very simple. Use the energy balance model. And this one is developed by Wagner and Eisman. The nice thing is it has coupled with a thermodynamic ice model, which is very nice. And also for this simplified model, we can give the same amount of forcing. As shown here is a polar focus forcing, and in the two groups of the strategies. So long story short is if we check the temperature response and the CS coverage response, you do see the CS recovery or restoration in the winter focus strategy, even though it's a little bit less extent, both showing in the temperature and the CS coverage. So this is for winter, selected from November to February versus summer is May from August. So if we do the forcing, apply the forcing separately in each month and sum them up together, and what you see here is they end up with a quite similar response. And that tells me those, temperature or CS extended response has a quite linear behavior in terms of the forcing window, at least in this model. But it's nice because it can help me to understand why there's a difference between this summer focus versus winter focus strategy, right? So if we do this same type of monthly forcing in each single month, and what you see here is the time evolution for the temperature response, and this is the bar plot for the last year, and you see the maximum or largest response happened in the main forcing experiment, while the minimum in the November, and you have a gradual transition in between. So if we decompose those total temperature response into the direct response from the cooling forcing itself, plus the additional response from the feedbacks such as CS albedo feedback, right? And what we can get is in purple is the temperature response without the CS albedo feedback versus the temperature response only contributed by the CS feedback. So what you see here is this contribution from the albedo feedback dominates this variation in the monthly forcing experiment. Well, the CS albedo feedback it deals with the absorbed shortwave radiation. So if we check the absorbed shortwave radiation in these monthly experiments, they are matching each other quite well. The largest ASR response is happening in May. But if we do the offline calculation, right, we can also do a simple offline calculation to calculate the ASR response in each month if we have this idealized CS extension from the present day CS state. What you see here is there's a lag. What we actually found is the ASR response from the calculation, it has the largest response in June instead of May. But we made assumptions, of course. So those could be the directions to go to figure out what's happening in the EBM. For example, we assume the ASR response is limited to the first applied months, but what really happened in the EBM, in this simple model, is the May month is quite unique. It's unique, firstly, it has the largest CS expansion, and it's also unique is because the CS restores quickly during the forcing applied months, but the retreat is quite slow. So you got the CS day here in the next 2 following months where the solar radiation is actually peaks. So that jointly makes the May peaks up and lead to a stronger signal in the summer focus strategy. So I think I will leave the summary here, and thank you so much.
Thank you so much. Okay, well, it looks great like that. Great.
Okay, great.
So we're now going to follow this with a talk by Ocean Visions. Ocean Visions have done a fantastic amount of work on building something called basically the Arctic Sea Ice Roadmap. I was fortunate to be consulted. I wasn't part of the organising stuff, but lots and lots of input from many, many people over, I think it was over 18 months, a good old period, getting a lot of views from experts around the field. I'm not considering myself necessarily an expert in the sea ice, but I was just one of the voices. And we look forward very much to hearing from you, Bridget, regarding the outcome of that, or the output of that we can then all learn from. Thank you.
Hi, everyone. My name is Bridget Shayka, and I'm a program officer at Ocean Visions, and I'm excited to tell you about our roadmap. So I'll just quickly give an overview of Ocean Visions and the repair program in case you haven't already heard me talk about it this week, and then I'll tell you how we developed the roadmap. I'll give you a preview of what it looks like. It's an online interface, and then I'll share some of the findings just around the SRM results, but there are many more things you can read about. So quickly, Ocean Visions is a nonprofit, and we are focused on catalyzing innovation at the intersection of the ocean and climate crises, which we view as interlocking. And we are a field-building organization, and so we sit at the center of a network of partners that we leverage to facilitate connections and collaborations to pursue our work. And you can see them all listed up here. And as I mentioned, we view the ocean and climate crises as one interlocking crisis. So rising temperatures and increased CO2 have dramatic impacts on the ocean, and so here are just a handful of some of those impacts. And the last one on the list is increasing melt of sea ice and ice sheets, which will be the focus of my talk. And then it's also important to think about the reverse, so changes in the ocean are having innumerable impacts on the climate as well. And I also just want to point out that I'm going to be referencing mostly thermal stress here, and that's what comes up a lot, has come up a lot this week, but ocean acidification is another impact of rising carbon dioxide levels that is having huge impacts on the ocean and is not going to be addressed by SRM. So at Ocean Visions, we think about what we do from the perspective of what we call the 4 R's. So I'll just quickly highlight them. So number 1 is reduce. We all know this, it's been said many times, but it can't be said too many times. We must reduce quickly and dramatically. And so at Ocean Visions, we think about ocean-based pathways to do that. And then in addition to reducing emissions, we need to remove the carbon dioxide that's already there. And so we think about marine carbon dioxide removal approaches in our remove arm. And then in addition to reducing and removing CO2, we also need to think about some of the ecosystems that are already going to be impacted at the current state of the world. And so that's where the 3rd R, repair, comes in, which is where I fall and where this work falls. So this is thinking about stabilizing critical marine ecosystems to avoid tipping points, and I'll come back to that. And then finally, we can't do any of this without reach, which is thinking about building global capacity, so bringing in more voices, more areas of expertise, etc., into all of these different R's. So when we are thinking about the repair work, we are considering the fact that many critical marine ecosystems are already going to be impacted by the current level of warming and the current climate change impacts. So in the repair program, we are really asking, is there anything that can be done to stop some of these effects on these ecosystems? And so one way to phrase this are what are all the possible pathways that could forestall these devastating changes, and really from a lens of trying to prevent some tipping points in some of these critical ecosystems if they have tipping points. And I will highlight that over 50% of climate tipping points with global repercussions are located in the Arctic, which is why we're all in this session to think about the Arctic. And in addition, the Arctic is warming 3 to 4 times faster than the rest of the globe. And so because of the huge implications of a warming Arctic in terms of impacts in the Arctic and global impacts, we decided to focus our first ecosystem as Arctic sea ice. And so Arctic sea ice is being lost dramatically. These images on the right just give an example of visualizations of the 2023 extent compared to some global numbers. And losing sea ice decreases planetary reflectivity, which increases heat uptake. Arctic summer sea ice has declined 50% over the last 40 years. And importantly, summer sea ice is expected to disappear by the middle of this century under all emissions trajectories, if not earlier. And the complete loss of summer sea ice could increase global temperatures by 0.2 degrees Celsius, in addition to upending Arctic ecosystems, but also having global impacts. And although Arctic summer sea ice itself is not a tipping point, it does impact other tipping points, such as melting permafrost or the Greenland ice sheet. So there are many connections. The Arctic is not just up at the top of the Earth. And so we are thinking, what, if anything, can be done to slow this loss? So before I dive into the roadmap itself, I'll just highlight some of the principles that we developed for our whole repair program, not just the Arctic sea ice work. There are more on the QR code, but I'll just highlight about 4 of them. So all proposed approaches require additional research, development, and testing to know efficacy and impacts. Ocean Visions is not advocating for deployment of any climate intervention approaches. And dialogues, governance, and research and development must include a diverse set of perspectives and expertise. And developing research also requires developing governance, which there have been many conversations about this week. Okay, so the goal of the roadmap was to assess approaches that have been proposed to slow the loss of Arctic sea ice and to see what is known about them. So we began by casting a wide net. We formed an advisory board of subject matter experts from multiple countries with various types of expertise, and including a broad range of perspectives as well. And we conducted interviews and conversations with over 100 experts from 13 countries. We did an in-depth literature review, which lasted almost 2 years, ultimately. We developed a comparative framework with the assistance of the advisory board, and then we conducted webinars and engagement activities to really get as much input as we could. Once the first draft was available, we sent that out for review as well to a wide range of people who had not necessarily been involved in the process up to that point. And any feedback that we received was integrated into the draft that we published in September of last year. So this is the format of the roadmap. It's a website, and the QR code will take you there. I will show some excerpts from a few tables in a minute, and they come directly from the tab at the top called Summary Figures and Tables. So if you are interested in more details than what I share, you can go there. And so you can see that the approaches that we considered spanned a wide range of potential efforts. And so we, this illustration is also on the website, just a different version of a way of looking at the categories. So the categories range from solar radiation modification to ice management, so directly managing the ice, surface albedo modification, Arctic protection, so area-based protections, and then pollution management, which included carbon dioxide, methane, and black carbon emissions reductions or removals. So I'll just focus the rest of this time on the solar radiation modification approaches. So this is an example of what it looks like on the, for any given approach. We have some categories. You can see these are most of the SRM approaches that we included, some of which you just heard about. And within each approach, we say, we include information on the state of the approach, the knowledge gaps, and the first order priorities. And really we were trying to determine what is known and what is unknown. And so in the state of the approach, we include information on how the approach might be implemented or what people's ideas about it are, its potential impacts on, of course, Arctic sea ice, but also on temperature and other factors, the readiness of the technology, any ecological or socio-ecological risks and or benefits, and then any governance and justice considerations. And I will highlight that there are many unknowns in many of these categories, as I'm sure anyone who's studying these knows, and especially in the governance and justice areas. And where we found gaps in knowledge, those are what informed our knowledge gaps category, but then also our first order priorities, which I'll talk about a bit later. So this is just an example of what the actual content looks like. We include links to references and descriptions of our categories. And we also intend for this to be a living document, so it currently gets updated about once a month. I have lots of new content from the previous talks to add to it. And so there's a way to leave comments, and also if you have thoughts, you can also email me. I'll put my email at the end. So I'll quickly highlight some of the things we found just for the SRM approaches. And so first I'll show an excerpt from our sea ice table, since that's what we were really focused around. So you can see we have 6 SRM approaches. The category for all of them is SRM, and we say whether they might be applied globally or in the Arctic. But these 3 middle columns highlight some of the information that we know about its potential impact on sea ice. And so for some of them, there is positive potential. For some of them, there's work happening. And for other ones, it's conflicting results. But many of these don't have a lot of papers published. And then for other factors that we considered, we thought about when it's effective, as you just heard, might be important to know, estimated potential temperature impacts, what the technical feasibility. We focused on 10 years because Arctic sea ice is expected to be lost by the end of the century, if not sooner, and then some assessments of risk. But there were many more columns in this table, so you should go look at it all. And then I'll quickly highlight a couple first order priority examples. So for example, for SAI, thinking about what the potentials are for an Arctic deployment and also what MRV might look like. For marine cloud brightening in the Arctic, determining if susceptible clouds exist at a large enough scale, and for cirrus cloud thinning, determining if this could produce a large enough impact. For enabling conditions, there are needs for research frameworks, both on the physical implications, but also on social exit ramps and checkpoints. And then for engagement, there's a lot to be learned about previous work and previous recommendations, including some of these examples from the ScopeX Advisory Committee. So finally, I'll just close with we're using this work to build on and to move forward with. So we're trying to collaborate or lead efforts to kind of fill in some of these first order priorities and knowledge gaps, especially by building collaborations between scientists and thinking about research frameworks. So with that, here's the QR code again to the roadmap, and I'm happy to take questions later.
Bridget, great. Thanks ever so much indeed. And can I stress that that is a living document, and the QR code and continuing to engage with Ocean Vision so that that is it's as up to date as it can be is really important. So that, you know, we are a community, we're not huge, and I think sort of participating in things like this is really great. Now we're going to follow, and our final talk of this afternoon is going to be given by John Moore. John Moore, who I've got to know over several years now. From the University of Lapland and University of the Arctic, and in particular looking at sort of various other interventions that we haven't spoken a lot about over the last 2.5 days, but we're going to look at combined solar radiation modification and targeted ice sheet interventions to stabilise vulnerable ice sheets. John, over to you.
Yeah, thanks very much. And this is actually, in a sense, addressing some of the real-world kind of issues we might have, that none of these approaches are going to be anything like the magic bullet that kills everything. Everything's going to be a patchwork of marginally successful interventions, if we're lucky, that together might add up to a significant difference overall. But often people say, what does success look like? And I have to reply, it looks a lot like failure. So bear that in mind. My version of a success might be somebody else's failure. And we'll see where we go. Okay, so this is what we're talking about, the Amundsen Sea, and you can see a ship there for scale, quite conveniently. So this is a difficult working environment, first of all, to be said, and you work at nature's convenience rather than the other way around. As people have said, we were interested in this because the Arctic contains a lot of tipping points, and obviously the cryosphere is a particularly important one, and the ice sheet potential contributions to sea level rise come from northern Greenland and particularly the Amundsen Sea sector of West Antarctica. And it's also important to bear in mind that civilization only has begun during the Holocene. This piece at the top of the last 120,000 years or so, when we have an undisturbed flat climate, in very strong contrast with the previous, particularly glacial period, where the climate was varying up and down very rapidly. And it's thought that these alterations are strongly related to the stability of the ice sheets changing ocean circulation. So the thing is, are the ice sheets doomed? There have been a series of articles over the last couple of years using words like unavoidable and disintegration, which tend to suggest that, oh dear, we are fairly doomed when it comes to it. But of course, those don't consider the possibility of any interventions. The thing is, though, solar geoengineering, very much like this guy wearing his fur coat and hat, but holding a parasol in the night time and hoping to be cool, is a bit delusional. Because most of the energy over the last 200 years has gone into the oceans, and it's going to stay there for 1,000 years or so. So this also means that ice sheets don't care about greenhouse gases anymore, or at least parts of the ice sheet don't. And that's because they are essentially geometrically unstable, and they will be rolling down the hill unless we do something else, which is actually to support them on their inland parts. So if they don't care about emissions or solar geo, how does it work that I myself authored a paper that suggested G6 sulfur, this sulfur injection scenario, actually acted to stabilize parts of the West Antarctic ice sheet, which seems to contradict what I've been saying so far. It's quite interesting. If you look at the bottom panel that I've circled there in blue, you can see that the red curve, G6 sulfur, is significantly lower than the other scenarios, and this is the temperatures in the deeper ocean offshore of the Amundsen Sea. So G6 sulfur is particularly good compared with SSP 245, etc. So why does it work? It's not because of the radiative forcing, it's because it promotes easterly circulation off of the Amundsen Sea continental shelf, which is very critical in the upwelling of a deep reservoir off the continental shelf of warm, deep saline waters onto the continental shelf, which then makes its way towards the underneath the ice shelves, protecting Thwaites Glacier and Pine Island Glacier. So it's a second order effect. And the interesting thing was this was consistent across all 6 models that we looked at, and winds, of course, are something that can be not particularly well studied. Now, I said that these ice streams are unstable, particularly in these areas I've marked here, which are equivalent to about 5 meters of global sea level rise if they were to collapse, at costs, roughly speaking, $700 billion per year per meter of the sea level rise if it was lost. And if we look at the base of a cross-section through Thwaites Glacier, which you can see over here, you notice the bedrock is getting deeper inland. And this is the case on all scales. If we zoom in, you can see this line here, and you're not seeing the mouse. Okay, sorry about that. But the ice is unstable on this reverse sloping bed. But you notice it's rough, of course. The real world has got lots of these nice little ledges that the Thwaites Glacier, being a good climber, is able to hang on to and cling on to these ledges. But obviously, at some point, it's going to fall off. And the question is when. We don't really know. All of the ice models, such as they are, give estimates ranging between, it's too late, we've already fallen off, to we can manage for 200 years. We're very much at the border of knowledge here. So what we also proposed, in addition to the usual SRM, etc., is this concept of a seabed curtain, which is this example here. In a cold room, you have a curtain keeping the cold air and allowing the big vehicles to pass through it. And the big vehicles you can kind of think of as icebergs flowing backwards and forwards. So what happens, here we see a cross-section through Thwaites, and you can see where the ice starts to float and the bedrock getting deeper, further inland. And over time, the deep warm waters in yellow cause the ice to retreat very rapidly. But if we block that deep water, the glacier essentially thickens and can re-advance up the slope because it's no longer being melted at the base by the warm, deep waters. So, if we look at a very advanced ocean model of the Amundsen Sea sector, in here you see the continental shelf and this deep warm water in red, and hopefully this video will play. You can see the circulations, and on the left side we build this curtain at 500 meters depth, and the waters inside are blue compared with the ones on the control run with no curtain. And so we believe we can definitely cool those deep oceans. When we plug this into an Earth system model, into an ice sheet dynamics model, consider a lot of parameters that we can change, such as when the curtain is built, the length of the curtain, dates of deployment, how fast the ocean heat is warming, etc. In a lot of different model runs, because we need to try to explore this parameter space, we can have a look at what might happen to the future of the ice sheets. And if they cannot be stabilized but still slowed, it can be very important in terms of cost benefit and lower migration pressure. The IPCC estimates that there is a low probability that 1 billion people will be forced to move by the year 2150 as a result of rapid sea level rise. So what we calculated here is a cost-benefit analysis of the sea level rise as a function at the bottom of when we decide to put the curtain in, and as a function of the size of the curtain. And the square boxes are the useful ones. And this is if we limit temperatures to 1.5 degrees above pre-industrial at the year 2100. Now, this is what you get if we don't. If we limit temperatures to only 4 degrees above the 20th century, we get significantly lower effectiveness. It's 3 times more effective if we can keep those temperatures lower. Because, as I call it here, the difference is in the damages between mostly intact, and I'm not just talking about Thwaites being mostly intact, I'm actually talking about civilization, in effect, the coastal defences, and that give a quadratic damage function compared with mostly broken, where you're talking about both the ice sheet and the coastal defences, and you're increasing the damage is just individually making things worse rather than having neighbouring effects, and so that's more of a linear function. So we wouldn't try to go to Thwaites immediately. We imagine a series of tests that we could perform on smaller scale, easier accessible locations. And we originally were thinking of going to Jakobshavn, but our simulations on Jakobshavn suggest it's the most unstoppable glacier on the planet now. There's nothing we can do about it. But that's, of course, for now. If Thwaites and Pine Island become significantly unstable, there's nothing we can do about them. So, to go back to this location, we probably have about 30 years or so to try to build a curtain in this location, or do all of the other things that might work as this kind of patchwork of a solution that's just about possible. But everything is going to be a massive challenge, but the consequences of not managing this, I think, pretty much spell the end of much of what we think of as civilization as it stands at the moment. Thank you.
Wow. Okay. What I do suggest, can I just ask the speakers to grab a chair? We'll come to the front. Do we have a roving mic for questions from the audience? Otherwise, I'm going to be running around. Is this the mic in this room? Okay, fine. Right. So we've got 15 minutes, and in order to include as many people in the discussion as possible, if you could please keep your questions brief, and I have asked our dear panelists to keep their answers brief as well, because that's the way that we'll ensure that we get as many voices as possible. So I'll take the first question, please. I'm going to take it from an early career researcher. So Yashas, please.
Thank you very much, Shaun. I hope it wasn't it was a biased decision to pick me first. But my name is Yeshis. I'm from the Center for Climate Repair in Cambridge. My question is to John. How do you see an implementation of a curtain, and what are your thoughts on some of the ideas like bubble curtains?
So I think that the materials, the engineering details are, of course, to be figured out. And that's the whole point of having a staggered step ladder, that we will look for off-ramps all the time as we go. I think one of the key issues is we don't want to introduce any damage or minimize the damage to local ecologies. So we are not keen on introducing things like plastics down there. We would like to have purely natural fabrics that you would have a biodegradable footprint. But all of those engineering details, we don't really know. But we do have specialist engineering companies that regard this as doable. They just want the science to decide what it is we want to build.
Great. Okay, next question. Alistair, a younger researcher.
I think I might be older. I'm 27, if that helps. Question mostly to, I guess, Matthew and Xia. Are there physical reasons to think that the Antarctic response to MCB or MCT is very different to the Arctic one? Just thinking about how balanced one could make these scenarios if balance was an issue.
Yeah. So far, what I showed is an idealized model. It's actually, representing half of the hemisphere. So both hemisphere in this model is assumed to be the same. But I'm currently working on, GCM using CSM to hopefully we'll have an answer for that. So for sure, I don't have an answer.
I also don't have an answer. But I think for the amplified winter warming in the Arctic, that's specific to the Arctic, and that would not happen in Antarctic, right? But I don't know, in terms of the cloud responses, I don't have an answer.
And marine cloud brightening might be more of a challenge in the middle of Antarctica as well. But minor problem. Any other questions? Yes, Ben, please.
For John, with the seabed curtains, have you been thinking about or envisaged the challenges or the opportunities potentially of doing this under UN clause in the Arctic, and then the challenges of doing this under the Antarctic Treaty in the Antarctic eventually?
Yeah, I mean, they wouldn't be under UNCLOS necessarily because they're obviously within the exclusive economic zones of the particular countries, which is Greenland, of course. Greenland obviously is governed by the Greenlanders. That's 100% clear. We have talked to them, and we've said that we won't go there unless they invite us in. We don't need to go there immediately. There's lots of places we can do all kinds of tests without going there. The Antarctic Treaty, yes, that's 29 countries, the rich country club, as I call it. But they will all, of course, have, except Switzerland has a coastline, and they will all be impacted by massive rates of migration. I think they have to look at, as I said, the IPCC estimated 1 billion people that could be on the move. That will have dramatic impacts. And I think there's a lack of understanding of the potentially imminent demise of these huge sea level rise elements.
More questions? One over the room.
Hi, sorry, I'm an outsider. I'm a philosopher, biomedical research ethics by training, and I'm from Argentina. And I would like to ask John a little bit more about the Antarctic, and because Argentina has, as I understand, part of that. Could be possible to test this in a region like under Argentinian jurisdiction?
Well, all the countries who signed the Antarctic Treaty System put aside national claims. I think that you could theoretically do all kinds of tests on any glaciated fjord, and you wouldn't go straight to Thwaites Glacier. There would be a staggered set. Like any of these interventions, you would build up your knowledge. What you need to have is this stratified flow. So you've got warm waters underneath cold waters. And then it just depends on what it is you're testing. Are you doing an engineering test? Are you doing an efficacy of thickening the glacier? What exactly are you doing? We have a lot of work to do over the next 30 years.
More questions? Can we get the microphone? I will run.
Yeah. I guess comment and question mostly for Matthew. So when I do impact studies, so I was really interested to see the results from the Arctic MCB runs. So the question is, when will that data be available? Because I'm really interested to see what are some of the other impacts around the world. And two, I noticed in the slide, I think when you were looking at the Sahel precipitation, it seemed like the characterization where it was like the monthly kind of cycle of rain. I think it was in like average daily precipitation, which doesn't mean anything to like on the ground. Like your average daily precip doesn't mean anything. So I would just suggest framing it in total monthly or total annual precipitation. Answers might be the same, but that's a more useful impact measure to see, is it actually changing rainfall in the region? So yes, that's the comment, and then the question is, will it be available?
Thanks for the comment. Definitely good to know. And yes, in terms of data, obviously make it freely available. I need to clean it up first, but yeah, I'll send it to you.
So, John, I do want to kind of press you on answering Yashas's question, which was, okay, there's curtains made out of material, but curtains made of bubbles. And leaving aside the actual practicalities of how you make them, what's your view on the likelihood of usefulness of bubble curtains?
I think there's all kinds of things you might do to improve the physical or the effective size of a curtain. You could imagine all kinds of spoilers, like dealing with hydrodynamics. I'm not an engineer. I think that's entirely up to people like you, Hugh, to tell me. I could tell you what size of curtain we need to have. And if you can make it physically for 1/10 of the size and have 90% of it made of bubbles, I'd be delighted. I think I would like to know what the effect on the ecology is of these bubbles and things like that. I can't really tell you any more at the moment. We need to have students and professors like yourself doing the work to find out.
I mean, it is quite. There are interesting trade-offs between how much energy is required to put these things into place, and how much energy perhaps is required to run them. So if you're doing bubble curtains, you have to keep them going, whereas if you're putting in something in situ, then it sits there. Anyway, yes, you're right. Lots of questions to be answered.
Great, Sumitra.
Thank you. Simple question. I came across this MCB, but not MCT, which is, so tell me what's the implementation, how the implementation goes about MCT, and any adverse impacts, unintended adverse impacts are there or not? Just
implications for MCT. I think. Yeah, I mentioned a little bit in the intro slides. And one of them is, we're mostly focusing on the polar night. And where we know, as Matthew already mentioned in his presentation, the Arctic is warming rapidly, right, than the rest of the globe. But if you check the seasonal warming, it actually warms the most in the polar regions, in the polar night, sorry. So since the initial results I got is more like the CS or the surface temperature, air temperature is quite sensitive to the first thing you applied. And some of the talks I heard is also I would say the temperature response is always mostly sensitive in the winter season. So what I want to, I guess my point is more like the temperature, to address the temperature cooling in the winter season is one of the implications for the mixed phase cloud thinning. Does that answer your question? I don't want to keep it too long.
So I'm going to take the chair's prerogative and ask a question. I want to bring Bridget into this, please. We have answers from the others. So
I just compiled all their work. They should answer.
No. So, Bridget, my question to you is, over all of the potential interventions that you looked at, could you just give us a flavour of because we didn't go into the details, but of just some of the approaches that you've included in your assessment or in your roadmap?
Yeah, so for SRM, I had put them up there, but I'll just say them again quickly. So we were looking at mixed phase cloud thinning, marine cloud brightening, SAI, and CCT, all of which were mentioned today, in addition to sunshade, since people have proposed those. But then for some of the direct ice approaches, we were looking at ice thickening, or people have considered relocating icebergs or blocking ice export. And there's one other one that for some reason I'm blanking on. And then for surface albedo modification, on the topic of bubbles, people have considered bubbles or films. People have considered things like tiles or glass microbeads or various other ways to reflect sunlight. And I think those are all of the more intervention-y approaches. The other ones, the most interesting other ones, I think, are black carbon reductions from wildfires and shipping.
Wow, what a good memory set. Okay, fantastic. Yes, please, Bruce.
Just a quick question on marine cloud brightening in the Arctic. How many ships would it take? You have this thing which said how much, roughly how many ships would it take to actually do that? And if you're given the go-ahead, what's a reasonable, maybe not an optimist, but a reasonable time period for actually getting it implemented and up and running?
Great question, and I think we don't have a good answer. We don't have a good answer for MCB in general, so we also don't have an answer for MCB in the Arctic. So yeah, I'm afraid I can't really give you a ballpark. Yeah. I think it'll be more than 5. The number of ships that Rob Wood came up with for, I think it was a degree of cooling, was 10,000 ships. Yeah. Of that order.
Yes, your name as well, please.
Hi, I'm Diego Villanueva. So yeah, from the sites. So one question: you have a long list of methods that could work in the Arctic. Like, there's this method of cocktail geoengineering. So, for example, if you combine MCB with SAI, of course, they will block themselves because you basically just have one sun, right? So, have you looked at how they interact with each other, whether some of them block each other, and is there a combination that could actually enhance themselves? Have you looked at that? Anyone?
I think that's still an open question. I know some people are thinking of doing cocktail geoengineering in models, but yeah, it's still an open question whether it works or not. Yeah, that's
great. Okay, further question from Alistair, please.
Sorry, I'm being selfish with questions. Bridget, there's a question for you, and thanks so much for your roadmap. I think it's brilliant. I guess to continue the road metaphor, are we ready to take the off-ramp for any of these ideas yet? And I might point, for example, to the recent shutdown of the Arctic Ice Project with their microbeads, if I'm getting that right.
Yes. So I'm not sure that I'm necessarily the one to decide about whether we should take the off-ramp for any of these yet. But you're right, there was a group that did decide to take an off-ramp recently. They were working on the hologlass microbeads idea, and they had done some ecological tests that they found resulted in potential ecological impacts, and they decided that, among other things, was a reason to not continue pursuing that approach. And so I think just having examples of people actually using off-ramps is really helpful in thinking about how we pursue a lot of these other approaches and research. Yeah.
Could you pass the microphone to John, please?
Yeah, just to emphasize that, this is evidence for the slope, in fact, being sticky and not for it being slippery. Because, of course, any ethical research will report bad results as well as good ones, and ethical scientists will realize that we have to stop doing that.
So on that, John, I'm going to ask you a question again. So Chair's prerogative number 2. When we talk about public engagement, and the scientists, engineers have got a desire to do an experiment in somewhere, when that permission is not granted by local people, I've heard some people say, well, you failed in your public engagement. And my question to you is, actually, surely that's wrong. We haven't failed at all. In other words, we've listened to the local population, and actually if they don't want it, then actually that is a good outcome. Got to go and find somewhere else, but is that not actually potentially an ingredient of good, an evidence of good public engagement?
Yes, absolutely. It's at the end of the day, it's up to the local people to find some benefits in what you're proposing, and if they don't, I think there's plenty of examples of people doing the sea ice thickening that you can ask other places, and people can have. They're not a homogeneous mass. People can have different opinions in different places.
Well, we've actually hit the 3:15 time, so this is the time where we're going to close this afternoon session. Before I thank our speakers, if you have had your appetite for cryospheric sorts of research whetted, can I therefore encourage you to look at what Hugh Hunt shared with us earlier this morning, which is the Arctic Repair Conference in Cambridge at the end of June. Applications absolutely open. We would love to see as many of you there as possible. It will provide a sort of yet more energy, slightly different topics being included, and some different voices in particular as well. So we'd really encourage you to see that. And then I would like to thank our fantastic panel this afternoon for their contributions and keeping us entertained and informed. Thank you.